Okay, we're going to look at how we calculate the pressure or volume or temperature of a gas after a change has been made using what we already know about Boyle's law, Charles' law, and Gay-Lussac's law. Before we get into that, just to kind of review, we can predict how a gas will change based on what we know about pressure and volume and temperature from those three gas laws. So, for instance, let's say we got this atmospheric scientist making a cloud in a bottle. The volume of the bottle does not change, so volume is constant, but pressure is increasing. Pressure is increasing. We want to know what happens to the temperature. Oops. Get that out of the way. We know what happens to the temperature. So is it going to go up or down? All right. Well, if I go look at my gas laws, which I have down farther here, Gay-Lussac's law says that pressure and temperature follow each other. They go in the same direction. So if my pressure is increasing, my temperature should increase. If my pressure is decreasing, my temperature should decrease. All right. So if I come back up here, if my pressure is increasing, my temperature should increase with it. And hopefully that makes some sense. As pressure is going up, that means more force is hitting the inside of the container. That means that those particles have to be moving faster. They got to have more impact from having higher kinetic energy. And that just basically comes from, well, higher temperature. Okay, so our temperature inside our bottle should be increasing. Okay, so we can use the gas laws like that to predict how something will, increase or decrease for a gas as something else is held constant. We usually focus on two variables at a time, like pressure and temperature, or pressure and volume, or volume and temperature. Okay, but what if we want to know what the new temperature inside this bottle would be? Okay, we start with some pressure and some temperature, and then we go and change the pressure. It increases to some amount, and then we want to know what's the new temperature going to be when this change is made. Well, we're going to need some math for that, and we're going to need equations to go along with these gas laws. So that is what is kind of down here next to these relationships with the arrows. Let's start with this. Okay, so Boyle's law is not just a, if pressure does this, volume does this kind of relationship. It's also mathematically shown here. All right, so pressure and volume are related such that if pressure is multiplied by volume, in one instance, should be equal to the pressure and volume of the gas multiplied at a different time when some changes happened. Since pressure and volume go opposite ways, if I have some pressure and some volume, and I go and increase my pressure, my volume has to decrease in order for us to level back out at the same thing on the other side of this equal sign. All right. If my new pressure is decreased, and then I'm wondering what happened to my new volume, it has to have increased in order to kind of, again, come out to be this same level here. Okay, now to figure out what exactly this pressure or this volume would be would take algebra. And while a lot of people have some algebra knowledge, this isn't really a math class, and if we can avoid doing some algebra and get to the important part, then that's okay with me if it's okay with you. So I've rearranged these equations already so that pressure and volume are alone, where we're looking for the new pressure or the new volume here. Okay, so we would do this with algebra. So for example, let me pick a different color. If I were to divide both sides by my V2, well, that would get rid of this V2 here, and I'd be left with P2. That's how I get this equation right here. All right. If I were to instead divide by the P2 on both sides, well, those would cancel out, and I'd be left with V2, and that's how I get this equation over here. Okay, so in this case, I've just kind of saved the step of doing the algebra to get P2 or V2 alone. So we can jump straight to it and say, I'm going to use this equation to either solve for the new pressure or to solve for the new volume that I've got here. Now, the other equations for these other gas laws get a little bit trickier. Scroll down here. All right, as soon as you have things divided by each other, the algebra gets way worse, especially since we've got things divided on both sides. So trying to toss things around, it just gets to be way more work than it's worth for what we need it for. So instead, again, we're going to kind of jump straight to it. If I'm using Charles' law and I want to find what the new volume of the gas is going to be after a change in temperature or volume has happened, I can find the new volume with this rearranged equation from this original here. Or I can find the new temperature by using this version here. Just to be clear, P is standing for pressure here, V is standing for volume, and T is standing for temperature. The little 1 here, or here, or here, means before the change has happened. It's kind of our original version of the pressure or volume or temperature. The 2 means after the change has happened, so it's going to be our new pressure or new volume or new temperature. Okay? So I can use these equations. This is kind of like my tool belt of what I can tackle. So let's look at some examples. Back up here. Whoop, too far. Okay. So I've got a gas, and I start with a pressure of 1 atmosphere and a volume of 2.50 liters. And then I make some change where the pressure increases and gets to 2.00 atmospheres. Then I want to know what the new volume is going to be with that. Okay, if I'm changing the pressure, how is the volume affected? What's going to be the new volume in liters? Well, okay, I need an equation that has both pressure and volume involved. Temperature is not involved. Temperature is held constant, so I don't want any T's in my equation. Okay, and I also want to make sure that I've got V2 alone. I want to find V2. So let's see if I can get an equation for this. Well, if I've got pressure and volume and no temperature, that's definitely going to be Boyle's law. Well, and if I want to find the new volume, V2, this equation looks like it would work pretty well. So P1 V1 over P2 equals V2. Now, if you have two variables next to each other, like this P1 V1, these are being multiplied. So P1 times V1 divided by P2 is going to be the answer that I'm looking for. It's going to give me my V2. That's what I'm going to calculate. Okay? So let's try that. P1 times V1 divided by P2. All right. P1 times V1 divided by P2 is going to equal my V2. Well, if I replace these variables with what I know, well, my P1 is 1.00 atmospheres. My V1 is 2.50 liters. liters. These are going to be divided by my P2, which is 2.00 atmospheres. 2.00 atmospheres. Okay, and the rest is just calculator work. So if I take, clean this up a little bit, my 1 times my 2.5 divided by 2, that's a 2.00, not a 2.06. 2.00, I should get my answer here. So 1 divided by 2.50 is going to be, 1 times 2.50 is going to be 2.50. If I then divide by 2, Well, I might need a calculator for that. Let's see here. 2.50 divided by 2.00 is going to be 1.25. 1.25. Okay, well, what are my units going to be? Okay, well, there's a couple ways I can think of this. One way, well, I'm starting with atmospheres for pressure, and I end in atmospheres. My volume starts in liters, and I should end in liters. And the problem even tells me here that I should end in liters. Now, the problem's not always going to ask you or tell you what the new unit is going to be, so you have to kind of be careful. Okay, well, one way you can kind of be sure you get the right answer in the right units is that our units need to be consistent. Whatever our units for V1 is, need to be the same units for V2. I'm not going to change halfway through and be like, well, maybe I should do milliliters instead. No, we're going to stick with liters. Another way you could see it is that when we do our math, whenever we were converting units, when we had a unit kind of get canceled out, it was because we had something on the bottom. Like if I start with grams and I want to get rid of grams, I'm going to multiply it by a conversion factor with grams on the bottom. In this case, I've got atmospheres on top and atmospheres on bottom. So those are going away. What's left is liters. So liters would be the unit I end with. Okay. Now, we don't always have to use liters. Like in the next problem, we're going to be looking at milliliters. All right. And we also don't have to keep using atmospheres for our pressure units. Atmospheres is popular with chemists. I tend to like it because the numbers are nice and easy and small. And if you're at typical atmospheric pressure, just from day to day, that tends to be around 1 atmosphere, which usually doesn't change your math a whole lot. 1 times 2.50 is just 2.50. So that's kind of nice. But there are other reasons that we might use other units of pressure too. Okay, so one popular one that also tends to kind of show up in chemistry is mmHg. This stands for millimeters of mercury. Millimeters of mercury. All right, on the periodic table, mercury is Hg, and millimeters as a unit is mm. So mmHg is millimeters of mercury. And we mean this pretty literally. The way that we used to measure atmospheric pressure, and we don't really do it often this way anymore, with a barometer, we would basically have a dish of mercury. And this is a simplification, but we'd have a dish of mercury. Let's see if I have a gray I can use for my mercury. I don't want to lose my blue. Back there. Okay. So I've got a dish of mercury. Now I forgot to change the color. Come on. There we go. Got the mercury in here. All right. And we had a tube sitting inside the mercury like this. Not a very good tube, but whatever. We would just see how far up the tube the mercury went as air pressure pushed down on the liquid. So as the pressure pushed down the liquid, it would go up through this tube, and you would just measure how far up the tube it went. And you'd measure that length in millimeters, and so your pressure would be literally millimeters of mercury. Okay? So aside from the history of it, that's just another unit of pressure. All right? So don't be scared of that. The math isn't any different. You're still running the equation the same kind of way. The only difference is what the unit looks like and how big the numbers are. Millimeters of mercury tend to be pretty big numbers. Another pressure unit that you might see is kPa. This stands for kilopascals. Kilopascals. This one's pretty popular with physicists because it's a little bit easier to convert out of because the unit means more than just kPa. We can kind of break it down to the units of force and area that make it up. For chemists, it's okay. But again, I'll always prefer atmospheres. But in any case, whether you're starting with atmospheres or mmHg or kPa, we want to make sure that unit comes out on the other side too. We're not going to change pressure units, halfway through the problem. So if I start in kPa, I want to end in kPa. If I start in mmHg, I want to end in mmHg. Okay, so don't let the new units scare you. Same goes for volume. Again, we could use regular old liters, we could use milliliters, we could use cubic centimeters, we could use cubic deciliters, all kinds of stuff. All that really matters, I guess I shouldn't have said cubic deciliters, it'd be cubic decimeters. Sorry, cubic deciliter doesn't make any sense. But whatever volume unit we use doesn't really matter as long as we are consistent, and we probably want to stay in metric. Okay? The only picky unit we have to be very specific about with these gas law problems is temperature. You'll notice the temperature here is in Kelvin. Kelvin. All right. And we do this for a very specific reason. When we're calculating things with temperature, like volumes or pressures, if this temperature were something like negative 10 degrees Celsius, and I plugged it in like that, or negative 10 degrees Fahrenheit, and I plugged it in like that, well, there's a chance that I could end up getting and calculating a negative pressure or a negative volume, which doesn't really make a whole lot of sense. I can have some volume, I can have no volume, I can't really have less than no volume. It doesn't really seem to make sense. And same kind of goes for pressure. It doesn't really make a whole lot of sense to say I've got negative pressure. Maybe in some terms of physics, there's a way to kind of turn it around and make sense of it, but it's not worth it. It doesn't make enough sense here. And so we avoid the issue entirely by using Kelvin, because Kelvin has no negative temperatures. We basically just take degrees Celsius and bump it up by 273.15 so that we no longer have negative temperatures. And then we get whatever that would be in Kelvin. Okay, now we don't need to do any temperature conversions here, but it's just so you know, all your temperatures are always going to be in Kelvin. There's a reason why you're not going to see Celsius and Fahrenheit in these problems. And it's because we're trying to avoid getting negative pressures and negative volumes. Otherwise, this doesn't make sense. Okay. Well, while we're on this problem, maybe we'll try this one. Okay, if V1 is equal to 1.50 liters, T1 is equal to 273.15 Kelvin, and V2 is equal to 5.00 liters, calculate T2 in Kelvin. Okay, so I'm looking for a T2 here. I've got V's and T's. I've got volumes and temperatures. So I need a gas law that has volumes and temperatures, and I want to be solving for this T2 here. All right. Well, Charles' law seems to fit that bill, where I've got volumes and temperatures. Okay, and if I am solving for T2, I will probably want this version right here. Okay, where I've got T1, and this is times V2 divided by V1 should get me my answer as T2. All right, so let's use that equation. T1 times V2 divided by V1. T1 times V2 divided by V1 equals my T2. Okay, so now I'm going to plug in what I have here. Let's do that. That's going to be equal to all right, my T1 in this case is 273.15. 273.15 Kelvin. Did not make that division bar big enough. Times my V2, which is 5.00 liters. Divided by my V1, which is 1.50 liters. Well, all right. So if oops, I don't need to put V1 down there. What am I doing? Just 1.50 liters. Okay, so if I take this and I plug it in my calculator, 273.15 times 5.00, right, that gives me 1,365.75. Then I divide by 1.50, and I get 910.5. All right, well, what are my units going to be? Well, my temperature started in Kelvin, so I'm going to end in Kelvin. So 910.5 Kelvin, big K, is going to be my answer. And this is my T2. This is my new temperature of my gas after it changes. Now, I can check my answer a little bit. Okay, Charles' law says that volume and temperature should follow each other. Okay, if one of them increases, the other increases. If one of them decreases, the other decreases. So let's see if that checks out. Oop, too far. Oop, come on. So my V1 went from 1.5 to 5. My volume increased. My temperature went from 273.15 to 910.5. It also increased, which makes sense. If I got a smaller number, then I would have a cause for concern. I would want to check my math. Okay, let's do one more example. Let's look at the second to last one here. Right? If T1 equals 525 Kelvin, T2 equals 300 Kelvin, and P1 equals 85.0 kPa, calculate P2 in kPa. Okay, well, if I've got pressures and temperatures, I would say that calls for Gay-Lussac's law. All right, so I've got my original equation here. We rearrange it, so either I'm looking for a new pressure or a new temperature. Okay, in this case, I'm looking for a new pressure. So I want P2 to be alone. I want it to be isolated. And this looks pretty good for that. I've got P's and T's. Volume is left out because it's being held constant. So if I take P1 times T2 divided by T1, I should get my answer, my new pressure. So let's try that. P1 times T2. P1 times T2 divided by T1. Right, and that should be equal to my new pressure P2. So let's plug in what we have. I've got T1 and T2 and P1. So let's do the P1 first, just because that's the order we've got it in here. So P1 is going to be 85.0 kPa times my T2, which is 300 Kelvin. And that's going to be divided by my T1, which is 525 Kelvin. So if I go and plug this into my calculator, 85.0 times 300 is going to give me 25,500. If I then take that and divide it by 525, I get 48.57-ish. And I can round it down if I want to. 48.57 kPa. Now let's see if that makes sense as an answer. Well, I started with 525 Kelvin for my temperature, and my temperature dropped to 300 Kelvin. Well, Gay-Lussac's law says that pressure and temperature should follow each other, just like my Charles' law does. So, let's see. Did my pressure go down? Yes. I went from 85 kPa down to 48.57 kPa. So that checks out. That looks like a likely answer for my new pressure. So this is my P2, 48.57 kPa. The rest of these problems basically follow this same kind of run. If you're not given numbers, we're just kind of, again, looking at the relationship between pressure and volume and temperature. And if we have values to plug in, we want to find the right gas law based on which unit or which variables we have, which properties we've got measured. What's being held constant is the thing that we leave out, the thing that we ignore. And then I just plug in what I have into the equation that allows me to solve for what I'm missing, like P2 or V2 or T2. Okay. From there, it's just plug it in your calculator. Whatever units you start with is what you end with, and you've got it done.